we go. Let me get started, guys. Haha, no. People always think that, but it's no candy.
You sure?
What? Yeah. All right.
How you doing today, Professor?
Pretty good. Let's see here.
Pretty good.
What section are we in here? We're in
306.
section 1. Let's see here. All right. 6858. So you guys have a good weekend?
Yes, did you?
No.
Yeah, pretty good. Didn't get quite as much done as I wanted to, but all right.
What happened to the cookies?
Oh, they found them.
I told you to find them.
Yeah, they found them.
How?
Oh, it had 2 minutes.
2 minutes.
Wasn't long. They found them. Found the cookies.
Wow.
I'm gonna bring them to school though. Then I'm gonna let them find them.
Professor Donahoe?
Not really.
Do you know what it looks like?
No. I don't know. I mean, I may have seen him once upon a time, but I don't know everybody.
I sprained my ankle, so at least you know.
Ah. Oh my goodness. Well, that's bad. All right, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Again, just ask you to bless this class. Just help us to glorify you in what we do. Help us to just enjoy math, which is part of your creation. We thank you for that. And I just pray that you be glorified in whatever we do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so some examples. Applications here. So I'm going to talk about just some simple applications of linear equations. Example 1, you have a race car wins 500-mile race at 140.7875 miles per hour. How much time elapsed? So if you had a 500-mile race and the race car had an average speed of 140.7875 miles per hour, you know, math books have a way of writing applied problems in like really dumb-sounding ways. This is certainly no exception. Like, all right, I'll stop complaining. All right, so the speed, the velocity here, v, is the distance over the time, right? But we can also sometimes write, I mean, we can always write, as long as the velocity is constant, that the distance is also equal to the speed or the velocity times the time. There is a distinction between speed and velocity, and for those of you who go on to take Physics 201, you will learn this distinction. And then, so what are we trying to find here? We're trying to find the time, right? So solve for t. T is equal to d over v, isn't it? And so the distance is 500 miles. And the speed is 140.7875. MPH means miles over hours. So what happens here is the miles cancel, and you're left with hours. Now, I need a calculator for that. I don't know about you. Now, the book asks us to give the answer to within a thousandth. So what would the answer be? let's see here, 500 divided by 140.7875. This gives us well, 3.551451. 14516. Da, 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 da. All right. Now that's not the answer. The book said to give it to within 1,000th, right? So that means that much, right? The question is this last digit right here. Do we round up? Do we round down? Do we do anything? Well, no. We leave it like it is because the next one's a 4. If it was a 5, we round up, or bigger, but it's not. So the answer is 3.551 hours. All right. Next problem. You have $970 invested. And a yearly rate of 11%. All right. The question is, how much interest is earned after 1 year? How much interest earned after 1 year? So the question is, what equation relates these things, right? Yep.
Is the equation, are you asking for the equation?
Go ahead. Yeah, if you want.
Equals PRT?
That's it. I equals PRT. That's exactly the one. So principal times rate times time, right? So here the principal was 970 bucks. I is interest. $970. The rate, 11%. So do I put 11 there? I mean, I wish, right? I wish. No, 0.11. I mean, goodness gracious, can you find a bank that'll give you 11% on your investment ever? Probably not. But if you want to lose 11% on an investment, it's really simple right now. You just take money, take it out of your pocket, just put it right here, and wait a year. 11% gone, just like that. Poof. It's called inflation. Anyway, which of course is not happening. It's transitory, right? Sure it is. 1 year. Fun fact, I may have told you this already. $100 in 2005, if you could take that $100 and put it in today's money, $150. That's how much inflation there's been in this country since 2005. Now, if we continue on the path we're on right now, it'll be worse. But anyway, 970.111. Now, so this is because we're going for a year. If you had like a half a year, you'd put a half year instead, right? Okay, if you had 4 months, you'd put like 4 over 12 there. Anyway, so what do we get? 106.7. So that means $106.70. That is the interest you'd earn, right? Hypothetical, if you had a credit card and for some reason they charged you simple interest, none do. But if you did have such a mystical credit card and you spent $970 and then you didn't pay it back for a year, ignoring all kinds of other draconian ways the credit card company's trying to take your money, just on the basis of interest and the money you owe, you'd owe 970 plus 106. You'd owe like, 1,076.70 after a year, right?
I have a question.
Yep.
This P, price, I could.
Principal.
Principal.
Yeah. So principal, abbreviated. Example 3. Put it over here for you guys. You got a rectangle. You're given that its width is 44 centimeters. You don't know its length, and you're given that the perimeter is 180 centimeters. Question, what's the length? So how would you solve such a problem? We do some word problems in here on occasion. My focus is much more on algebra, but we do some applied problems here and there. Well, yeah, I mean, let's think symbolically here. This would be what? You got W up here, you got L here, right? So the formula for the perimeter would be twice the length plus twice the width, right? So then we can solve for L, right? L equals to 180 centimeters minus 2 times the width. What was the width? Well, 44. And then we have to divide by 2. Let's see here. That's 180 minus 88, which is 92. 92 divided by 2 is 46. So the answer is 46 centimeters. That's what you got? All right, good. You freestyled it? Yeah. I used to freestyle when I was like a little kid. Yeah, we'll talk more about my rapping career as we go on in here. We're not quite to the right place in class. But there will come a time we will discuss my skills, or lack thereof. Let's see here. What's that? No, I mean, as much as I ever did. But I can say that much. Okay, that is it for applications. Did you enjoy it? Okay, good. Don't worry, we'll come back. There are applications of quadratics later this week. Let's see here. So next up, complex numbers. So this was section 1.2. Now I'm in section 1.3. So I probably won't cover everything in section 1.3 in complex numbers. I'm just going to strategically tell you a few important pieces of information about it. So first of all, here's the notation. C is a plus bi such that a and b are real numbers, and I is the square root of minus 1. So what's that say? I squared is what? Is negative 1, right? So this is the set of complex numbers. Now, we need to talk about this because we're going to talk about solutions to the quadratic equation, and you need complex numbers to complete the story there. Like, it's just part of the story. It's unavoidable. All right? So let's see here. Example 4. What would happen if you calculate I to the 4th power? Let's see here. How about that? That would be I squared times I squared, right? Which would be negative 1 times negative 1, right? Which is 1. That's funny. I to the 4th power is 1. Another interesting thing about I is if we have I times I is minus 1, that means that minus I times I is 1, right? So if you divide that equation by I, what happens? This tells me what? This tells me that 1 over I, well, it tells me that minus I, right, is equal to 1 over I. That's kind of weird, isn't it? I mean, it's definitely foreign to our experience with real arithmetic. You don't like flip a fraction, flip a number, and then get it to be negative, right, when it was positive before. The trick here, though, is that complex numbers are really neither negative nor positive. There's no ordering of complex numbers like there is for real numbers. Not any nice ordering, anyway. Example. This is more for breadth. It doesn't even really probably come up in your homework or the course, honestly. So example 6, what if we had I to the, I don't know, 83? Could you do that one? How about this? That would be I to the what? I to the 80 times I to the 3, right? 80 plus 3 is 83, and 80 is 2 times, or what is it? It's 20 times 4, right? So that's I to the 4th raised to the 20 power. And then you've got I times I times I, right? I. I to the 4th we just got done saying is 1, right? So 1 to the 20 power, still 1. So it's just I times I times I, which is what? We've got I times I, which is minus 1, right? And you got an I. So the answer here is minus I.
That holds true for every even number?
Well, how does it go for different powers? You just kind of have to look at it, but I to any power, it's either going to work out to 1, minus 1, I, or minus I. Those are the 4 possibilities. I could start listing them. Since he asked, let me ask him. Since Francisco asked, I will just begin listing them. I to the 1 is I squared is minus 1, I cubed minus I to the 4th is 1, I to the 5th is I to the 6th is minus 1, I to the 7th is minus I to the 8th is 1, I to the 9th is I, and so forth and so on. It's always this cycle of I minus 1 minus I 1, I minus 1 minus I 1. It just keeps cycling every 4 powers like this. So if you have I to a power in your homework, there's 4 possibilities. How many tries do you get in your homework? Oh, only 3. Ooh. If you're just going to guess, there's like a...
I mean, you can do it again, though.
No, maybe I'm just joking. All right. Example 8. What if we were to take 3 plus 2i and multiply by, let's say, 11 minus 7i? How would you multiply complex numbers? There's a homework problem like this, but I think otherwise it doesn't really come up past this point in the course too much. So the answer is use the distributive property. This is 3 times 11 minus 7i plus 2i times 11 minus 7i. So I just use the distributive property. What I'm really just saying right now, guys, is just to FOIL it out. You just multiply it out like usual, except the unusual thing is what? There's imaginary numbers. So 3 times 11 is 33. 3 times 7 is 21, minus 21i. And then you got plus 22i. And 2 times 7 is 14, so I got minus 14. The key here, though, is the weirdness is the I squared. See, I squared, that is what? That's negative 1. So what you're really looking at here is this minus 14i squared is really minus 14 times minus 1. It's really a plus 14, isn't it? With I squared, what looks like is negative could actually be positive. Right? And vice versa. We can take something positive and make it look negative with I. But anyway, 33 plus 14 is what? 47. Thanks. And 22 minus 21. Hey, I can do that one. 1. Right? So plus I. There you go. By the way, 47 is the real part. And 1 is imaginary part of the number. If there is no real part, like if you have, for example, if you just had like 10i, that number is said to be pure imaginary. This is a pure imaginary number. The answer to the previous question is called a complex number because it's not, well, pure imaginary numbers are also complex numbers. So like these are not mutually exclusive categories. Like even every real number is technically a complex number because real numbers are a subset of the complex numbers.
First part of that equation,
Yeah.
line 11 minus 7i, is it part of the solution or is it just there?
What do you mean? I mean, the question here, example 8, was multiply these numbers.
No, like the 3 plus 2 and 11 minus 7, is that? I feel like I'm misunderstanding something.
The problem is multiply the complex numbers. So like, here's 2 complex numbers, multiply them.
Okay, so
That's all.
on the other side of that, that's the product of those. So that's like in factor. On the other side of the equal sign.
Oh, this is a factorization of that? Yeah, that's true.
Okay.
But we wouldn't factor complex numbers like that.
I got you.
Like, I wouldn't ask you the opposite question. That would be mean.
Yeah.
Like, I could say factor 2. Can you factor 2? I mean, obviously, 1 plus I times 1 minus I, right?
Yeah.
Multiply it out. It's true. Because you get 1 plus I minus I squared. So, I mean, there's neat things to do with this, but you're tempting me to talk about things I ought not talk about in here. This is a good question, but also evil because it's tempting to me as a mathematician to talk more about this. Yes? What?
What's the application of this?
Ah.
How do you use it?
So there are various applications. The one thing is, if we studied this more deeply, the length of this number and the length of that number is just the distance from the origin to the number in the complex plane. So like the distance 3 plus 2i, we go like over 3 and up 2. So this is like 3 plus 2i. 11 minus 7i, you go like over 11 and down 7. It's like down here somewhere. So the length of this from the origin is what? If you remember what's that? Square root of 9 plus 4, square root of 13 is the distance of the origin to this number. The distance from the origin to this number would be the square root of 11 squared plus 7 squared. Don't make me do that. The interesting thing, though, is the distance this number is from the origin is actually the product of the distances. So like, if this is distance 1 and this is distance 2 from the origin in the complex plane, this is distance 1 times distance 2 from the origin in the complex plane. And also something neat happens with like the angle, like if this is angle theta 1 and this is angle theta 2, this is angle theta 1 plus theta 2. So one application is just to describe like rotations in the plane. Complex numbers give us a nice way to do that. Now, perhaps a better answer is electrical engineers use complex numbers to model something called impedance. So like, if you talk about resistance for an AC circuit, you have inductors, you have capacitance, and then you have pure resistors. A complex number will give you the impedance, which describes the particular way an inductor or capacitor or some collection of them responds to an oscillating like voltage source. So that's one application. They're also just all over the place in math and physics. They're just unavoidable. They're not really, imaginary is an unfortunate term. They're no more imaginary than real numbers. They're very real in the sense of their existence, and they're useful for many things. They're also just unavoidable for algebra, so we have to talk about them. Yeah. Okay, so let me wrap this up here. I won't talk about them too long, though. So, like, this is the first section. I have gotten dragged into writing this up. I have disciplined myself to not write this before this point. You guys are a bad influence. But listen, if you want to know more about that kind of stuff, be a math major. Come and take my complex analysis class or whoever's complex analysis class, and we'll talk more about it in there. Complex numbers are important to mathematicians and also engineers and scientists and other people. Example 10. How about this? If we have the square root of minus 49, all right? Let me show you how we simplify this. This is the square root of minus 1 times the square root of 49. What's the square root of 49? 7. So the square root of minus 1 is I. So we have I times 7, which of course we can also write as 7i. So there you go. This actually is mostly what we need in here. Just this thing right here. This is most of the complex that you need for this course. I'll do another one. Square root of minus 137. So we do square root of minus 1 times the square root of 137. What's the answer? It is I times the square root of 137. That's it. So the point here is if we have the square root of a negative number, we can trade it for I times the square root of that number with a plus on it. Pretty simple. That's the larger point here is complex numbers allow us to deal with square roots of negative numbers. And that's why we're talking about it. So, did you get that? Okay, cool. I'll be back over here. We are now going to begin our systematic treatment of solving the quadratic equation. Now, good news for you guys is, because you're the third time I'm teaching this today, I'll actually do the right thing at the start. So example 12. Let me start out with just something really simple. How would you solve, excuse me, x squared plus 3x plus 2 equal to 0? The quadratic formula is incorrect. So I reject the quadratic formula as the answer here. No, I forbid it. I'm joking, mostly. Just partly joking, partly not. So we factor, right? So we have x plus 1 times x plus 2 equals to 0. Notice the appearance of the equals to 0. That was missing last week, right? I was talking about factoring, not solving. Now I'm talking about, yeah?
Oh, sorry, I was just waiting for you to ask them.
Oh, okay. So what do you think this, what are the answers then? How do we get this? Either,
So for that one, since you have two factors there, you
Uh-huh.
can separate it into two equations.
Uh-huh.
You have x plus 1 equals 0, x plus 2 equals 0.
okay,
And that equals out to x equals negative 1, and x equals negative 2.
very good. So the answer is, there are two answers, either -1 or -2 will do. Now, you're absolutely right. We could have used the quadratic formula, but this is way, way faster. Now, I very seldom do a proof in this class, but this is a place where I feel obligated to show you a proof. That's what's going to happen now. Here we go. Suppose we're trying to solve ax squared plus bx plus c equals to 0, where a, b, c are real numbers, and a is not equal to 0, okay? That's the generic form of a quadratic equation. I'm now going to show you how we can solve this by factoring for arbitrary a, b, and c. Let's see how it goes. So I'll start by dividing by a. This gives me x squared plus b over a times x plus c over a equals to 0 over a, which is just 0. So my first move is to clean up that coefficient of x. Right? I couldn't do this last week because we were factoring expressions, and you can't just divide an expression by a number without changing the expression annoyingly. But in equations, we can divide by numbers. So hooray, divide by a. All right, great. Now what? Now I do a very, very sneaky step. I do x plus b over 2a quantity squared. And if you think about that, that will recover the first two terms here, right? But what is x plus b over 2a squared? Let me write it over here. It's x plus b over 2a times x plus b over 2a, right? Which is x squared plus 1/2 b over ax. Let me just get to the point here. It's plus b over ax plus b squared over 4a squared. See, when you multiply it out, you get a half plus a half, which is a whole, right? So if I write x plus b over 2a squared there, to be fair, I must subtract b squared over 4a squared here. And just to emphasize here what's going on is what's underlined in red there is equal to what's underlined in red here. See, because I can take this equation and I can do what? I can just subtract this piece to the other side, right? And that gives me x squared plus b over a times x is equal to parentheses x plus b over 2a quantity squared minus that term. So I did that here, right? Yeah. Nope. So this step right here is what is known as completing the square. So when we complete the square, we take all the variable in the quadratic and we lump it into one term, which is squared. All right. Now, can everybody see this? If you've got a glare on the board where I'm writing, then like move. I can't tell. Like for me, there's a glare here right now from that stupid window. And I would just close the blinds, but we've experienced what happens when I try to do that. So so x plus b over 2a quantity squared, and then I'm going to make a common denominator of b squared minus 4ac, right, divided by 4a squared. That's equal to 0. So you see what I did? I multiplied this by 4a over 4a to make it match with that one. And then I had to pull a minus out because I'm keeping a minus in front. And the reason I'm doing that is because I have planned the next step as it follows. The square root squared. Remember, this is that same trick we did last class. Like if we wanted to write 6 as a square, we'd go, well, 6 is really the square root of 6 squared, right? I'm just using that idea again on this formula here. Why do I do that? Well, now I've got the difference of squares. So I know how to factor it, right? Because difference of squares, how's it go? X plus b over 2a plus the square root of b squared minus 4ac. If you don't mind, I'm going to divide by 2a there. See, because the square root of 4a squared I can just replace with what? Square root of 4, right? Times the square root of a squared, yeah? Which is 2 times what? I heard a, but to be careful, I really should put absolute value of a there. The reason that doesn't matter here is that's like plus or minus 2a. And because of the pattern here, whether a is positive or negative, it's just going to flip-flop these. So like it doesn't matter if we drop absolute value in this particular context. There it is. So same principle we did with example 12. If we do on this arbitrary one, it gives us what? Either this is equal to 0 or that's equal to 0, right? So if we take this whole thing and set it equal to 0, or if we take this whole thing and set it equal to 0, what pops out is simply x equals to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. You may recognize this. This is the famed quadratic formula. And perhaps ironically, I really don't intend for you to use it. Actually, what I want us to do is to follow the idea of the proof to solve problems, because that's a better way. You're like, what do you mean? Well, let me show you what I mean. I want to show you how to solve quadratic equations using completing the square. All right, so here's one. X squared plus 6x minus, I don't know, 20. Let's try to solve this by using completing the square. So can you guys complete the square on that one? What do I do? Yep.
Was it take half of the middle term and square it and use it as the third term?
Okay, so x plus what then, squared?
Wait.
I mean, you said it right. What's half of 6?
3 and
Th-
then square it.
3, right? That's squared, that's 9, so I have to subtract 9. Okay, that's right there, and then minus 20. Don't be like me, don't reject this method. I was stubborn, I refused to learn this when I was in college algebra. I didn't learn completing the square until I was in differential equations. And in doing so, I made myself an inordinate amount of work in all of the classes which followed, and I robbed myself of algebraic understanding in all the classes which followed. It was foolish, my obstinance on this point. I would always use the quadratic formula and like work my way backwards from this to the quadratic, to like the factoring. This is a bad way. This is a bad way. So I'm going to show you the right way, and I hope I can get you to do it. But okay, so then what? That's x plus 3 squared minus 29, right? Which is the square root of 29 squared, right? So we can write this as x plus 3 plus root 29, x plus 3 minus root 29. If we are looking at that equals to 0, we get what? X equals to what? Minus 3 plus or minus the square root of 29. So this, what I just did, I would say this is solving using completing the square and factoring. Okay, let me just write that out. This is solving quadratic equation using completing the square and factoring. All right. There is another way to use completing the square to solve an equation without factoring. We can instead use something called the square root property. All right, let me show you that way. So this is example 14, which is like example 13, but I'm going to do it a different way, okay? Watch this. So x squared plus 6x minus 20 equal to 0. So it starts out the same. I complete the square. X plus 3 quantity squared minus 9 minus 20 equals to 0. All right? And then here is where we part ways with my previous example. Now, instead of trying to factor it, I isolate the square. Isolate the square. X plus 3 quantity squared equals to 29. Right? And then the square root property says when you have an equation like this, you can take the square root of both sides, but there's fine print attached. You have to remember to put plus minus in, otherwise you lose half of the story. You're like, well, why is that true? I would remind you of example 13 where we derived it. So like x plus 3 is equal to plus or minus the square root of 29. So, taking square root of both sides. If you want me to be fussy, the reason is this. The square root of x plus 3 squared, you know what it is? It's actually the absolute value of x plus 3. And the absolute value of x plus 3 is plus or minus x plus 3. And that's how the plus or minus gets into the business. This is just a somewhat irrelevant side comment. The point I'm trying to get to here is solve for x. What do you got? You got x equals 2 minus 3 plus or minus the square root of 29. So which is a better way of doing it? Completing the square with factoring, or completing the square with isolate the square and take the square root? I don't know. It depends on what appeals to you more, really. They're about the same amount of writing. Yeah? Like when I was in your place, I probably would have liked example 14 way of doing it more than example 13 way of doing it, right? Actually, I already told you I was a slave to this equation over here when I was in your place. Example 15. So here we go. How about this? What if we had x squared plus, I don't know, 12x plus 42 equal to 0. We want to solve this thing, all right? So let's use completing the square, and then you guys decide. Do you want to use the factoring, or do you want to use the square root property way? Square root property way? Okay. We'll do both. I'm just which one we're going to start with. Okay, so complete the square. I got what? I've got x plus what this time? I heard a 6. We have a winner. Now, if I add 6 like that, that means I'm adding a 36, because 6 times 6 is 36, right? So to be fair, I must subtract 36. And then, of course, the 42 is still there. Now, I hear what the people want. I listen to your pleas up to a point. I mean, this stops working when you start saying things like, we don't need tests in here, right? Equals to what? Equals to, looks like minus 6, right? Yeah. Now, if we were in the world of only real variables and only real solutions, game over, end of story, we're done. It's impossible to have a real quantity squared equal to minus 6.
Oh, so that's what you gave the other problem there. I was wondering why you used minus 29.
Oh yeah, because we gotta, like the next move here is isolate the square, right? Isolate the square is the idea here.
I got you now.
Doing the same thing here, isolate the square, yep. Well, it would have been before, but I moved it to the other side, see? So this is x plus 6 squared plus 6 equal to 0. And then I isolated the square by moving the 6 to the other side, make it minus. Now I use the square root property. Square root property says x plus 6 is equal to plus or minus the square root of minus 6, which is what? Oh, good news. We reviewed complex numbers, so you guys are familiar with this now. We do what? Plus or minus I root 6. A lot of 6's in this problem. Don't worry, only two 6's, though we're okay. Plus or minus I root 6. And there you go. There's the answer. It's complex. So if your instructions said find the solution of these quadratic equations possibly complex, then this should be an answer you give, right? If the question says find all real solutions to the following quadratic equations, this one you should say there are no real solutions, because the solutions are complex. What does factoring look like for example 15? So factoring is involves a little bit of kind of creativity, let's say. So we complete the square. Right? And then see, it's like, oh, Oh. How do I use difference of squares when I have 6? How can you write 6 as minus something squared? Check this out. So 6 is minus 6i squared, which, by the way, is minus I times the square root of 6 squared. This is what I call a very sneaky move. I mean, you know, so this is x plus 6 quantity squared minus parentheses I root 6 squared. And then we can use difference of squares. And of course, what happens at the end of it, this tells us that x is equal to minus 6 plus or minus I root 6. Of course, we're going to come to the same answer once we go through the factoring. It's just, I do think factoring in this case is a little bit like harder to see through, but I do hope you could do this. If you're an A student. If you're a C student in here, like, I wouldn't be too surprised if you couldn't do this, and it wouldn't be the end of the world if you couldn't, but yeah. What's that? So, do you see the difference here? We isolate the square versus I actually go through the trouble of factoring x squared plus 6. I have to convert it to a difference of squares like so, and then that gives me this. Let's just, one more example for today. I think I'm out of time just about. What are the 3 cases for completing the square? Do you see the 3 cases? When we complete the square and we get done with the arithmetic, what could have happened? We complete the square and this one, right?
Yeah.
And after we complete the square, what happened? We had minus 29, right? That corresponds to the fact that we can actually factor it using real numbers alone, right? If after you complete the square, right, like here, you can see it more here, complete the square, we had plus 6. That means that the polynomial is prime. That means that you can only factor if you use complex numbers. What's the other thing that could happen? How about this? What if I had, like, oh, I don't know, x squared plus 20x plus 100. Complete the square on this. What do you got? Half of 20 is 10, right? Oh, did you got me? Okay. X plus 10 quantity squared, right? So I had to subtract my minus 10 squared, right? And then I still got my 100. Wait a minute. What's that? What's 10 squared? 100. So what happened here? So if your quadratic you're looking at happens to be just a factor squared, when you complete the square, it just factors it. So there it is. Yeah. And if we set this equal to 0, what are the solutions? Minus 10, right? Now, we like to think of that as being minus 10 repeated. That way I can say the following. Any quadratic equation has 2 solutions, right? Possibly repeated and possibly complex. Which kind of solution I'm in? It depends totally on the sign of this discriminant, right? B squared minus 4ac positive gives real solutions, or equal to 0. B squared minus 4ac negative gives complex solutions. All right. So Wednesday, we'll look at more of these and hopefully some applications. And actually, I need to get ahead. I'm going a little bit faster than I would like to, ideally, in this course at the moment. It's because, unfortunately, life has put on me a thing I have to do Friday, which is go and close on my house sale in Alabama, which means I won't be here Friday. But my plan for class is to post the video of Thursday morning's class, which should have more of the radical solution equation stuff in there. So what should you do with the time? You could come here and watch the video together on your tablets, which would be so exciting. Or better yet, you could come here and work with each other on the homework. Like, that would be the smart thing to do, right?
So I'm like,
So like,
we don't have class Friday, but we
Not-
can meet here and like have studies.
yeah, you can meet in here, have a study group. Nobody else is going to be here Friday, so you can use the room together to work on the homework. That'd be fantastic. I encourage you guys to work in study groups, by the way. Like, that's totally acceptable, fine. You know, work together. Make sure you find somebody smarter than you to work with, generally speaking. Like, if all the blind come together and make one study group,
And so much smarter.
the lost lead the lost. It's not.
They wouldn't know that because they feel like they were.
Hey, could you hit the stop record? You know what I'm talking about? The red. Yeah, there. Just hit that again.